Well, today we're going to look at other angle relationships. In fact, we may look at more than that. We'll probably look at some other angle relationships, and maybe even some other angle relationships. The first one is really just like our inscribed angle. The one we had in the last section works out pretty much the same. Remember, for an inscribed angle, maybe I should draw one. Remember, in the last section, we figured out that the measure of this angle here, we'll call it rho, is 1/2 the measure of this arc. Remember, the measure of this arc, just to refresh your memory, is the same as the angle measure of the central angle. If we had a center, say right here, and then draw these two rays, or say segments. In fact, they're radii, aren't they? Because they go from the center of the circle to the circumference. If we draw these two radii, the measure of this angle here is the measure of the arc. The measure of this angle, well, it's half the measure of the arc. That's because it's way over here on the circumference. Well, it turns out this one works the same way. It's almost as if you could treat the tangent as another chord. If you were to tilt this and turn it into a chord, you would have the theorem we just wrote down here. Well, this isn't a chord, it's a tangent, but at least one point of this line is on the circle. And in this case, it turns out that's all it takes. You got one point of this line on the circle, even though it's not a chord, we end up with exactly the same relationship. This angle here is half of the arc. And this angle over here, angle beta, the measure of that angle is exactly half the measure of this arc. And I would just remember it the same way as, just think of it as an inscribed angle. Technically, it's not actually an inscribed angle, but just remember that when one of the lines forming the angle is tangent, then it works just like if you got two chords with an inscribed angle. They work the same. Makes it easy to remember. You only have to remember one thing for two different situations. There's a proof, of course, otherwise it probably wouldn't be true. But it wouldn't help you any. I mean, it doesn't help you to remember it any, and it really doesn't make it any more clear, and it doesn't actually motivate you in understanding why this is true. At least I don't think so. There are some proofs they actually help you to see the sense of the theorem, or the fact, if you want to look at it that way, which makes it easier to remember. In this case, it's my opinion that the theorem really doesn't add anything to the situation. The easiest way, I think, to remember it is just think of it as the one we did in the previous video, where treat the tangent as if it were a chord, and exactly the same relationships apply. And we'll be using these in the problems coming up, so if you're not sure what this means, it'll become clear in the problems. I don't think you're going to have any trouble at all with this. This is the other angle relationship. Now there's an other angle. Sorry, I think I got cut out. I was saying angle relationship there. Now here's one that's it's kind of cool. Suppose the angle isn't over here on the circumference, and it's not a central angle. It's somewhere in between. These two lines intersect somewhere inside the circle, forming four angles. Remember, these are vertical angles, so alpha here, and this would also be alpha. This is beta, this would also be beta. Remember, these are vertical angles, so they're congruent. So whatever we say about this angle, we can also say about this angle. What can we say about this angle? Well, that's the cool part. It turns out that this angle is not half of this arc. It's not half of this arc. In fact, the theorem we have doesn't make it a fraction of either arc, but it does make it the average of the measure of both arcs. We have the measure of, hang on, sorry, I had an A on there, it's supposed to be DC. So the measure of this arc plus the measure of this arc, then you divide by 2. In other words, it's the average of this arc and this arc. Once again, the proof really involves triangles and not averages. It doesn't lead you to understanding why it turns out to be the average. I think that with more trigonometry in a more advanced class, you could show why this angle is actually the average of these two. And it's not that hard to remember, because if you look at it from the point of view of the previous theorems we had, you can almost lump it all into one theorem that holds for everything. And I'll show you what I mean by that. Well, if we drew these lines intersecting at the center of the circle, I'm not sure I guessed at the center very well, but pretend this is the center P of the circle here. What would be the measure of, say, this angle? Well, it's the same as the arc. The arc is, the measure of AB would be alpha, because the central angle and the arc subtended, the arc which subtends the central angle, they have the same measure. That's how you define the measure of the arc. Well, this one would also have the same measure, right? So, if I wanted to, I could write that 2 alpha equals the measure of AB plus the measure of DC, because this alpha is the measure of DC, this alpha is the measure of AB. DC, there we go. And that means alpha equals 1/2 plus the measure of DC. How does that compare to what we had before? Well, AB and alpha, the measure of AB and alpha are equal. So, pardon me, I should put parentheses here. This is really saying alpha plus alpha divided by 2, which is alpha. So this actually works. I can write alpha equals 1/2. In other words, the average of these two. And the average of these two is exactly either one. For instance, what's the average of 2 and 2? Well, it's 2 plus 2, which is 4, divided by 2, which gives you 2 again. The average of 2 identical numbers is just that number back again. Same thing happened in here. So you could, in this case of a central angle, you can write alpha as the average of the 2 arcs which subtend the endpoints of the crossed segments, or the intersecting segments. Okay. What about when it's over here, right on the circumference? Well, in this case, we could still write it this way. This is a point here. This is our opposite arc. Well, you could consider a point a pathological arc with a measure of 0. What kind of an arc would have a measure of 0? Well, a point would have a measure of 0, and that's the only one. So if you look at it that way, you could still write that alpha is the measure of BC plus the measure of A divided by 2. because the measure of A is 0, and that'll just give us back our original formula. So this formula can be used for every case that we've had so far, if it helps you to remember it that way. And again, we will be using this formula in the problems later. That should help to remember how this works out. And here's our other angle relationship. It involves exterior angles. And again, it works pretty much like the interior angles or the circumscribed angles, except you have to think of this one now as negative. If it helps, just remember when you're on this side, when you're inside the circle looking at the arc, it's positive. When you're outside the circle looking at the arc, it's negative. That's not very mathematical, but if it helps you remember, when we were on this side it was positive. On this side it becomes negative. If you think of this as negative, then you've still got an average here. Although I think I may have written it wrong. Let's see here. I did write it wrong. It's supposed to be BD here. No, the easiest thing to remember, when it's outside the circle, just take the large arc and subtract the small arc. You're always going to subtract the smaller one. The easy way to remember that is we can have negative angles in a coordinate system. For instance, if I lay out, pretend that's an XY axis. Now, let's say this is 45 degrees from here to here, and it's 45 from here to here. This is frequently listed as negative 40. In fact, it's pretty much always called negative 45 because we went in the wrong direction. We normally consider that counterclockwise to be positive, so this is a 45 degree angle. And this, going the wrong direction, would be minus 45. But for ordinary angles without a coordinate system, a negative angle really doesn't make any sense. For instance, if alpha were to turn out to be negative, that would be kind of senseless. It's either 0 or it's some positive number in a case like this. And that's the easiest way to remember that you always subtract the small one from the big one, because if you did it the other way, you could end up with a negative angle, and that wouldn't make any sense. Does this rule actually make sense? And what I mean by that is, as this point moves farther and farther away, alpha gets smaller. We've already figured that out. For instance, if it were inscribed, it would be half of what it was before. When it was here as a central angle, it was equal to arc BD. Now, as we moved it off to the left, that is, our vertex moved to the left farther and farther away, we keep these points fixed. If we didn't, this might not be true, but if these 2 points are fixed, so they have to stay right there, and we just keep pulling this out farther and farther away, so the distance from this point to these 2 endpoints gets larger and larger, then alpha gets smaller and smaller. So what has to happen as we move out this way? This part that we're subtracting has to get bigger and bigger, because this doesn't change. BD is fixed. But as this moves to the left, this arc, the part that we subtract, should get larger. That way, when we subtract it from BD, the actual angle gets smaller and smaller, which is what's supposed to happen. Now, is this arc going to get larger as we move this way? Let's take a look. Well, to make sure that we're moving it in a reasonable way, I drew a straight line. And we're going to move this vertex along this line. If we move it forward, this arc should get smaller. In fact, if we move it until it's just touching the circle, this arc becomes 0. Remember? As we move it to the left, what happens? Well, suppose we move it from here out to here. These segments become longer, and look at where the if I finish this off, it's a ray. Right now it's just a segment. But they go from B and D out to a new point here, which is a bit farther away. Where do they intersect this circle? Well, our arc AC now has gotten bigger, hasn't it? And that's what's going to keep happening. The farther we go to the left, the larger this arc will become. What's the limit? Well, like I said, we can't have a negative angle. So the size of this arc, as we move our vertex this way, the measure is going to approach BD. It'll never exceed BD. In fact, it'll never quite get to it except at infinity. As we go out to infinity, alpha becomes 0, and AC does become equal to BD, but that only happens way out at infinity. And in this class, I don't think we need to worry about that. We won't get to infinity. So the exterior angle will never quite be 0, but we can make it as small as we want by extending it as far away from the circle as we want. But just remember, when you're outside the circle, you got to subtract that second smaller arc. When you're inside the circle, you add both arcs together. And of course, divide by 2 either way. Well, this is, I don't know, kind of a weird problem, it seems to me, because it doesn't really make use of much of what we learned in the last 10-15 minutes about, well, especially in this case, we've got a chord and a tangent. They tell us the chord is definitely not a diameter, so this is not a right angle. Kind of looks like this is less than 90 degrees and this is more, but that's just the way it's drawn, and they're telling us right up front it's not drawn to scale. In other words, don't make any conclusions. I'd like to say don't draw any conclusions, but that doesn't sound right. Do not arrive at any conclusions based on the way it's drawn. So what do we know? That it's less than 90 degrees? Well, we don't really know that. Like I said, the scale it's not drawn to scale, so we can't make any assumptions based on the actual appearance. What about B? It's greater than 90 degrees. Well, again, we can't make that assumption. How about equal to 90 degrees? That's the one thing we know it definitely isn't. It's not a tangent. A tangent would be perpendicular, and you can't have multiple perpendicular lines at a particular point. If this is the point of tangency, then the diameter would be perpendicular at that point, and no other line would be. Well, there are longer lines longer than the diameter segment, that would be perpendicular, but they would be extensions of the diameter. What about the last one? Can we say it's not 90 degrees? Yeah, we can definitely say it's not 90 degrees because they definitely told us it's not a diameter. So, the only thing we know for sure is that it's not 90 degrees. That didn't really use the fact that this angle is half of arc BA, did it? No, it didn't. If you're trying to look for a way to work that in, I think you'd be spinning your wheels. And the only important part of this problem is knowing that it's not a diameter, so this can't be 90 degrees. This one's pretty simple. All we need is our exterior angle theorem. Remember, the exterior angle theorem applies whether both lines cut right through the circle, both lines are tangent to the circle, or any combination of that. Actually, there's only one other combination, isn't there? Or one line goes through and one is tangent. That exterior angle theorem applies to all of those cases, which means that this angle here, 29 degrees, must equal 1/2. Oh, there we go. 1/2 of the big arc, that's DG, minus the small arc, that's DF. Well, the big arc here is 114 degrees. The small arc we don't know. That's x. And this is all over 2 and equal to 29 degrees. That should be degrees there, and I guess that should be degrees too. So we do a little algebra after this and get that 58 equals, actually I wrote equals. That doesn't make any sense. There we go. One great big equals sign. 58 equals 114 minus x, so we rearrange and get that x equals 114 minus 58, which is 56. So this arc here is 56 degrees. Pretty easy. We just had to use that exterior angles theorem and we're pretty much done. Not really complicated at all. Well, this one is going to involve a little computation, isn't it? Unfortunately, they wanted to know which one is not true, which means a lot of these are going to turn out to be true, but we're going to have to figure out. For instance, what's angle 1? Well, let's see. They tell us that line L here is tangent at point P. That means that this angle is angle 1 would have to be half of the arc which subtends angle 1. And that's PQR, which is 220 degrees. So we have the measure of angle 1 equals 220 over 2. Well, that's what they say it is, so that one's okay. What about angle 2? Well, remember, forget about this part that's cut off here. Angle 2 is PR and this here, PL. So the arc is PSR, 80 plus 60. So the measure of angle 2 is the 80 plus 60, which equals 140. Pardon me, 140 over 2. Because a chord and a tangent, the angle they form, you compute it exactly the same way as you would compute an inscribed angle. And that turns out to be 70 degrees, and that's what they said. Okay. What about angle 3? Aha. Now we have an interior angle. And that should be the measure of QR plus PS, and then divide that by 2. So we have, for the measure of angle 3, we get 100 plus 60 over 2, which equals 80. So this one seems to be right. It's tempting to just assume this is the bogus one, but we better check. After all, I could have made a mistake over here somewhere. Measure of angle 4. Aha, another interior angle, which would be the average of 80 and 120. Let's try that down here. Measure of angle 4 equals 80 plus 120 over 2. Well, that's 80 and 120 is 200 divided by 2 is 100, and this is indeed, they put the wrong one way down at the bottom. See, if the wrong one had been A, we could have finished this problem a lot quicker. So the only one here that's not true is D. Everything else worked. Well, looks like those crazy congressmen are trying to do geometry again. Let's see what they got wrong this time. Well, let's see here. For this angle, we need to take this arc and subtract the measure of this arc, and then divide by 2. and see if we get 15. Now let's see what we can do to figure out what this arc is here. One problem with this is that we're not sure which of these to take seriously. Well, we got three things here that he seemed to have figured out. Which one's wrong? Well, let's do some calculating and maybe something will jump out at us here. This 50 degrees must be the average of BE and CD. That's from our interior angles theorem. So we've got, let's call this X. What the heck? So we have 60 plus X over 2 would equal 50 degrees, or 100 equals 60 plus X, which gives us that X equals 40. That means BE here is 40. Well, let's see how that works out. This angle here, 15 degrees, should be equal to 60 minus BE divided by 2. Remember, when it's out here, we have to treat the smaller arc as if it were negative. So we get 60 minus 40 over 2. That's 20 divided by 2 equals 10. But 15 doesn't equal 10. So that's one problem here. He computed this wrong, I would say. Or he computed this wrong, which is what we used to get to this. Or he computed this wrong. There's all kinds of things that could have been written down wrong here. For instance, if we're going to assume that this is correct, then this 60 minus BE has to be 30, which means BE has to be 30, not 40. If we assume this is correct, then BE has to be 40. But I guess the important part to this problem is they don't all add up. There's something wrong with the way he computed BE. Either this angle was measured wrong, this arc was measured wrong, or this was computed wrong based on something else. But at any rate, if you do it one way, BE is 30. If you do it the other way, BE is 40. So this set of numbers here, 15, 50, and 60, they just don't match up. There's lots of ways they could be wrong. But that's about all you can say, really, I guess, that they don't match up. Because if you try to use all these and put them together, in one case you get that this equals 40, in another case you get that this equals 30. And that doesn't make any sense. Well, here's one that looks kind of weird in the sense that we got too many things we don't know. For instance, we know that this is an exterior angle, so we can write that 60 degrees is equal to 1/2 of the big arc, FGE, minus the small arc, EF. So we could write that out. Oops, should have, the M is supposed to be outside the parentheses, pardon me. That's a little better. Now we've got the large arc, FGE, minus the small arc, EF. Well, we have one problem here. We've got two unknowns and one equation. Well, we could write this same equation for this one over here. That will give us another equation. The problem is, it'll introduce an unknown of FG and GEF. In other words, we'll have another line with two unknowns. And if we keep going, we'll get 3 equations with 6 unknowns. That won't help much. What else can we do? Well, since these are all tangents, that helps a lot. If these went through the circle, we'd have a problem. But they're tangent. And that means that if we take the three arcs that we're concerned about, say EF, FG, and GE, they cover the whole circle, don't they? Or we could say that EF, the small arc, plus the big arc, that's FGE, they add up to 360 because they cover the whole circle. So if we write that out, this out, what we can say is that, I think I've already said it, so we'll just write it. The measure of FGE plus the measure of EF equals 360. Or the measure of FGE equals the measure of, 360 minus the measure of EF. Well, we've got an FGE up here, don't we? That means we could just substitute and write that this is 1/2 of 360 minus the measure of EF minus the measure of EF. So when I substitute, and I can simplify this and write that 60 is 1/2 of 360 minus 2 times the measure of EF. I've gotten rid of this variable. Now we've got an equation with only one variable, and we can solve that. We can write, we'll multiply both sides by 2 and get that 120 equals 360 minus 2 times the measure of EF. Well, if I subtract 120 from each side, add 2 times the measure of EF to each side, and I'll get that 2 times the measure of EF equals 240, or measure of EF equals 120 degrees. We can write that in over here. You see, this wasn't too hard. First you had to understand that this angle is 1/2 of the measure of this arc minus the measure of this arc, which is what we wrote up here. And then we had to find a way to get rid of one of the unknowns, which we did with this relationship. After that, everything drops out. Now we can do exactly the same thing here, except that we don't have to go through all this all over again. Well, for this one, we've already figured out the relationship between FG and GEF. They add up to 360, and we can get exactly the same setup here, where we can write that 80 equals 1/2 of 360 minus 2 times this, FG. So we multiply by 2, do a little arithmetic, and get that 2 times the measure of FG equals 200, or FG equals 100. And of course we can do the same thing right here, where we get that 40 equals 1/2 of 360 minus 2 times the measure of EG. Multiply both sides by 2, do some arithmetic, and get that EG is 140 degrees. So does this work? Well, let's see here. We got 120 plus 140 is 260 plus 100. Well, that's 360. And since there's no blank spaces here, in other words, EG, GF, and then FE, we just come right back to E. These three arcs add up to the whole circle, which is 360 degrees. So, our numbers at least make sense. Notice something else about this that's kind of odd. The sum of the angles inside a triangle is 80 degrees. Or pardon me, 180 degrees. The sum of the angle and the small arc that it intercepts, those add up to 180 also. This is 180, This is 40 and 140. This is 60 and 120. In other words, the arc measure is equal to the sum of the two opposite angles. And we also know that, for instance, this is an exterior angle. This exterior angle is equal to the sum of the two opposite angles. So what's with all these relationships? Well, I'm going to let you play with that a little bit and try to figure out why in the world the measure of this arc plus this angle would add up to 180, or conversely, why in the world the measure of this arc would be exactly the same as the measure of this exterior angle. Well, that's about it.